Thank you and welcome to part 3 of the Siemens Seminar Series brought to you by Siemens and Rains. Part 3 has two parts. The first is a presentation by myself, Geoff Currie, looking at an introductory primer to artificial intelligence and machine learning in nuclear medicine. I guess that the first thing to do is to actually thank Siemens for their sponsorship and making this series available. And of course to all the RAINS members and others who are tuning in to listen to the presentation. With the COVID-19 crisis, it was really important that we're able to provide some means for us to get together and add to our learning and our capabilities, and I think that Zoom provides a bit of a platform for that, but we couldn't do it without Siemens and the hard work of many others. So I guess that we'll move on to today's presentation. And as I said, is that the topic is looking at an introductory primer on artificial intelligence and machine learning in nuclear medicine. And I think the key thing here is that the purpose of this is not to actually arm the listeners with any deep capability in performing machine learning or deep learning research or to develop neural networks. It's really about recognizing the fact that artificial intelligence is here. It's been here for a long time. We just haven't been calling it that by the same name. But it's been in nuclear medicine for a long time. Traditionally, we lead the sort of technological development. And one of the important things is to realize that we're sort of getting a little bit left behind compared to radiology around the AI, machine learning and deep learning front. But critical to this presentation is to arm people with the confidence to have the discussions. So if you walk into a room and there's a bunch of people talking about doing research with artificial intelligence, then a lot of people just turn around and walk away because they don't feel like they actually have the skills or the capability or the knowledge to be able to engage in that conversation. And you do, we all do. It's not as complicated as you might think. It's just using a different kind of language. And so the purpose of this particular presentation is to target those novices that just want to have enough insight to be able to be part of that conversation, to engage in the conversation and feel like you're part of it. When you develop a research team to do an artificial intelligence project, you don't need everyone in the team to actually have skills and capability around developing neural networks. You need a couple of people with that kind of capability, but you need other people with capabilities around clinical and technical skills and capabilities as well, and to make that well-rounded team to come together. And so, but if it is AI based, well then using the language in those discussions really gives you a little bit of confidence and capability to drive those projects forward. So forgive me if some of what I say it sounds a little bit basic or fundamental. That's what I'm actually aiming for. I can certainly do subsequent presentations that take a deeper dive into neural networks and machine learning and deep learning. But for now, the purpose of this is to actually really look at that grassroots level so that people can start to be confident about engaging in conversation. So what is artificial intelligence? It's a pretty broad term. And it's a broad term that sort of captures almost everything we do. I've got golf clubs that have been designed by artificial intelligence. I don't know what that means, but we have artificial intelligence all around us. A lot of machines that are designed and programmed to do things are called artificial intelligence. It pops up across the community. It's a very broad term. If we think about nuclear medicine, the phase and stroke volume images that were produced on our old gated heart pill scans, the auto contouring of regions of interest around kidneys or left ventricles, the polar maps that are generated as part of your quantitative software packages associated with myocardial fusion SPECT scans, circumferential profiles on the old thallium scans decades ago. All these things are a form of artificial intelligence. But that's not what we're really talking about. When we talk about artificial intelligence, that kind of artificial intelligence has been embedded in nuclear medicine for a very long time. But we're talking about a specific kind. And so a subsegment of artificial intelligence is machine learning and artificial neural networks. And a subsection of that where RL is representative learning. We're sort of going to skip over that today and focus more on the next step, which then is to using convolutional neural networks and deep learning. So that's the language that we're going to be focusing on today, because ML and neural networks and DL and CNNs are the language that you're actually seeing in journal articles. And when we start to think about the AI cycle, and what's really important is that if you go back to, November last year, so November 2019, December, January, we actually started to see a real emergence of interest in artificial intelligence in the nuclear medicine community. And we saw a number of publications starting to emerge in the journals. European Journal of Nuclear Medicine Molecular Imaging, the JNM, the JNMT. And then when COVID-19 sort of hit, it sort of took a bit of a back seat while everyone was sort of focused on getting COVID-19 journal papers out. So I think we'll see a return to the interest around AI. But this is a bit of a diagram that shows the cycle that's associated with, any sort of frontier technology, but in this particular case, AI. So the purple line is our typical frontier technology curve, where we get this initial hype, and we can sort of, in the brackets, I've sort of labeled it against Maslow's hierarchy of where we might be, but in reality, we're talking technology. So when we start to think about this hype, there's this psychological need. We get excited about it, and we go from 0 to 100 fairly quickly. But then we actually start to realize what the real capabilities are, and we have this trough of disillusionment that occurs. And then after that trough of disillusionment, we get a bit of a second wave that comes in that forms some sort of reality, and then it sort of plateaus off to what its productivity will be, or what it's actualized to actually be. The AI cycle, and specifically talking machine learning and deep learning in medical imaging, at least, so nuclear medicine and radiology, is a slightly different curve. So we actually see the innovation that occurred, back in the 70s. We had an initial hype. There was actually a bit of a low spike because we really didn't have the capability and the technology to sort of integrate it broadly. So it wasn't a huge hype. And so as a result, the trough of disillusionment was also not as sharp and not as deep. And the recovery back out of it was actually relatively quick as well. And so what we actually had is, after that initial disillusionment, we had this period of enlightenment. And this is what nuclear medicine's good at, of actually going, here's this great new technology. We get a little bit of a hype to start with, but then we actually get realistic about it and start to think, how can we really use this to benefit our patients? And so this is this enlightenment stage. And so it's this, our second hype is where we are. We had this second hype coming in. And then out of the second hype, you actually know that there's people out in industry who, are skeptical about the role of artificial intelligence in nuclear medicine and radiology. Others are ready to embrace it. And so we get this delicate balance between, our hype enthusiasts, our fast followers, and then our skeptics. And this part of the curve kind of represents that, where our fast followers are on the downslope, and then our skeptics are at the bottom. When we actually move along, I think that I've put on the line of where I think we're actually currently at. And as a profession, I think nuclear medicine is where the green dot is. So we're starting to come up the upslope. And I think radiology is where the blue dot is. So they're a little bit ahead of us, and we're playing a little bit of catch up. So when we think about radiology and machine learning, we're thinking about the opportunities for machine learning to determine, I guess, which number or which ones of the huge number of radiomic features could be used either on its own or in combination with other radiomic features to determine an outcome, and or to get the best outcome. And we need to remember that this is not as simple as multivariate analysis, where you end up with 15 variables, and we sort of do a multivariate analysis and work out that 2 or 3 of these variables collectively predict an outcome, because that's what our human brain is capable of actually digesting. and synthesizing. But what we do with neural networks is we work out that, okay, in fact is that there's only two of features that are important, because the third one, even though in multivariate analysis it showed a relationship, in fact it's redundant because it's telling us the same thing as one of our other variables. So we come down to two variables and reduce the error, but then we actually work out that we weight them differently. So it might be that the best outcomes achieved with variable A with a 20% weighting and variable D with a 70% weighting. And we don't get that kind of information coming out of multivariate analysis. So it illuminates those relationships, and it helps us to consider how our semantic analysis fits in with our radiomic analysis for improving patient outcomes. And then we take a step further with our machine learning. We can start to think about image segmentation, lesion detection, referencing historical images, generating reports and second reader systems, and deep dives into data mining. Also, our business analytics are really important potential applications that we're seeing in radiology. So if we think about the spectrum that we have in radiology, and we need to think where nuclear medicine is in this zone. And so we have our normal visible spectrum of red through to purple. And within that, we're moving from sort of predicting things through to automating things, and then, of course, adding some perception. And so we're starting at things like as simple as business analytics to moving through detection, localization, classification, and then with the automation, it's triage, segmentation, radiomic feature extraction. And then we start thinking about perception, that quantitation reporting, and a really important application we're moving towards is dosimetry and calculating radiation dosimetry around therapy doses as well. But we know that not everything operates on the visible spectrum. So in the infrared zone, so below this prediction area, we have a kind of a situational awareness zone. And this is where we might be using things like small data. Small data is actually really important. We all get bogged down with big data and doing multi-center trials and all those sorts of things. And while those things are really important for that external validity of any form of research, including neural network analysis, is that there's a whole bunch of opportunity that's really rich in small data. If I do a project, then sometimes that project is purely focused on me being able to improve the outcomes in my department. And so to be able to actually have improved outcomes for my patients, regardless of whether it fits with the rest of the world or not, it doesn't matter. So I can actually use small data to make changes locally. So small data is important. And of course, as I kind of alluded to in the previous slide, using artificial neural networks and machine learning in parallel to conventional statistical analysis. And then of course, at the other end of the scale, up in the ultraviolet zone, we move beyond perception and start thinking about judgment and authentic intelligence. And of course, when we talk about human in the loop with artificial intelligence, this is really important because humans make those judgment decisions. And it's really crucial that we recognize that requirement of the human in the loop. But nonetheless, is that the developments around deep learning, there's some quantum neural networks that are starting to being developed, and with quantum computing, there's the potential to start to develop improved judgment of machine learning and deep learning systems. Certainly co-registration and image reconstruction, and I'll talk about image reconstruction later in the presentation. But importantly, decision making, and where does decision making fit in? Can we rely on artificial intelligence making decisions? We've seen, AI-driven cars that make decisions autonomously from the driver that can be catastrophic at times, but it could save their lives. There's another one. I guess that it's how we program them. Is that if these are highly programmed systems to make decisions, while it may make a decision independent of the driver of the motor vehicle, is that it's not making it independent of the person who programmed it to make that decision in that way. And so I guess that my son likes to talk about in terms of using the car as an example, that if you've got an AI-driven car, then we've programmed that car to make decisions or take actions based on certain situations. So if it detects something in front, then it brakes. If it detects something to the side, then it might swerve to avoid it. But when it's actually starting to make autonomous decisions, so once you've got an autonomous thinking car, then you might actually have a car that decides that to avoid killing 4 people that are walking along the side of the road, it actually has a crash that kills the driver, right? So you think when you program a car, it's programmed to protect the driver. If you actually had a motor vehicle that was genuinely autonomous, then all of a sudden it would actually learn along the way, and it would actually could make a decision to say, well, the driver is asleep because he's letting the car drive itself. But I have 2 choices. I either hit those 4 people walking along the side of the road and potentially kill them, or I swerve to miss them and hit the tree or the truck or whatever's beside them and kill the driver. And it will make a decision. 1 death is actually better than 4 deaths, and then autonomously make that decision. So there's a lot of grey areas and a lot of concern about what would happen when we get to genuine synthetic intelligence. But we're a long way from that point. And I think when it comes to medical imaging, there always needs to be a human in the loop. So why are we getting excited about all this stuff? Is that, annually there's this ImageNet visual recognition error rate that's determined. And you can see that it's decreasing over time. You can see the trend there with the blue line. The red line represents the human error rate. And so the human error rate's about 5.1%. And around about 2016, for the first time, the artificial intelligence outperformed the human. And so that's when we actually saw that second hype, this enthusiasm to say, well, okay, well, maybe we're onto something here. And so, and we've seen it continue to decrease. So we're sitting at about a 2% error rate now. And, it'll slow down. It's not going to improve much over that. So law of diminishing return. But I think what I wanted to point out in this slide is we all focus on this 5.1% error rate of humans. But surely if all of a sudden we're developing neural networks and deep learning algorithms that outperform humans, then we need to be looking at how they're outperforming humans. What is it that these convolutional neural networks are seeing that the humans are missing? And I'll talk a little bit about that later on as a few examples. And then do we retrain humans to start to think, or at least to look at the things that that machine learning is actually looking at? So, so what we should see, represented by the red dotted line, is that maybe the human error rate will improve along the way as well. As I said before, nuclear medicine's sort of fallen by the wayside, and this is a Medline search at the end of 2019. The only search was for machine learning, but you can actually see that, and we'll see similar things with deep learning and other keywords, but you can actually see that nuclear medicine, PET and SPECT, that are typically leading the way in technological advances and the publications around those, are a long way behind ultrasound, radiology, MRI and CT. Importantly is that some of the applications in MRI and CT, they overlap with the applications in PET and SPECT. And so while this particular graph, doesn't paint a pretty picture for today, what it actually does tell us is that there is so much opportunity in SPECT and PET, and generally across nuclear medicine. There is an enormous amount of opportunity for us to develop tools using artificial intelligence. So I've mentioned this whole idea of semantic analysis and radiomic analysis, and just to quantify that or to qualify it visually, when we actually think about how we do, and we'll tack in AI into this later in the presentation, but when we think about how a physician does their reporting now, is that they have their imaging, CT, MRI, PET and SPECT. It's processed, it's displayed, and then the physician looks at those images and has some sort of determination about what's going on. But at the same time is that, that process, there might be some segmentation associated with a lesion of interest. We may actually extract some features. So there might be some quantitative software, and a really good example of that is the cardiac software packages. So then you end up with this radiomic analysis. It could be some SUV data, for example. And so then the physician actually brings those two things together in the reporting. So the semantic analysis associated with what they're looking at, and the radiomic feature analysis that has also been done, and interpret it and create the report. And so what we need to do is see where artificial intelligence fits into that. Obviously, part of it would be these two purple areas could be driven by artificial intelligence, which would be one of the approaches. And so if we think about a system perspective, then we need to be thinking about, and one of the differences perhaps that I've found between radiology and nuclear medicine is that a lot of the strategies that are developed around radiology fit the personalized medicine focus, whereas nuclear medicine tends to focus more on the precision medicine aspects of things. But you can see here that the whole idea is, how do we actually use artificial intelligence with our little data on the left and our big data on the right to actually improve our evidence-based practice, improve our precision medicine, and as a result, improve the outcomes for the patients. And the outcomes for the patients may actually be increased survival, a disease-free period, might decrease their costs, increase their quality of life. And you can see within the diagram that there's different things, is that using this system perspective, we provide personalized medicine in a patient-facing environment. But at the same time, we provide precision medicine through a pathology-facing environment. And all of that obviously is driven by evidence-based practice. Our randomized controlled trials feed into those things. And so if we cycle that around, it's all about learning and improving. So now that we've painted the background, let's move forward to neural networks. And essentially, a neural network is sort of an image analysis algorithm. It's not just an image analysis algorithm. When we talk about convolutional neural networks, then they're looking at image analysis. Whereas an artificial neural network itself, it can be a series of connected nodes of hundreds, thousands, millions that actually look at data that's inputted. So it's not necessarily an image. It might be actually data that we input. And I'll show you some examples as we move through. And those nodes receive information from the nodes before it with different weightings. And the idea is to adjust the weightings on those nodes to maximize the correct answers. And so we train that neural network to get the best outcomes, so the best or the least error. And what that does is it adjusts the weightings, and then we can test it for its accuracy before it's implemented in the real world. So what I'm going to do now is go through a very superficial look at how a neural network is trained and works. There's a couple of references on the page there that you can read, particularly the bottom one if you're interested in a little bit more depth of how a neural network works. And there'll be a third article that will come out next year in Seminars in Nuclear Medicine. Seminars in Nuclear Medicine is doing a special edition on artificial intelligence in nuclear medicine. And there'll be another similar article to these two that looks at the mathematics associated with machine learning and deep learning in nuclear medicine. So if you're interested in the deeper look, then go to these journal articles, and forgive me for what's going to happen on the next few slides, because we're really just looking at it from a superficial level. And so if we look at a standard artificial neural network, this is not a convolutional network, we'll get to that. This is an artificial neural network typically associated with what we call machine learning. And what we actually have is we have a large set of data. Let's say that we have 1,000 patients. And we might split that data into 800 patients to create this large data set that we use for training, and 200 patients that represent this smaller data set that we're going to use for validation. And so each of the patients actually has their patient details, age, weight, height, all those sorts of things. You know, blood test analysis, radiomic feature analysis from different kinds of scans. They could have PET spect and CT and MRI data. They might have biomarkers and outcome data. And so all of these become data like an Excel spreadsheet that we can enter in. So it's data, it's not an image. And we have a scaling a layer, so an input layer that converts this data into the kind of information that the neural network recognizes, which is, you know, numbers. And so we input all this into our neural network. Then we have what's called our hidden layers or our fully connected layers. And within our fully connected layers, which are our purple ones, then each of these nodes is connected to every node in the next layer. So this node up the top here is actually connected to all 6 of the nodes in the next layer. And then we pass this information through these nodes, and each of these nodes has each of these pieces of information as an input. So this could be, let's say it's 150 different variables. There's 150 different variables that come in, and each of these nodes receives 150 bits of information, right? And they all come in with different weighting, and these weightings can be adjusted. So we forward propagate that information through the neural network, and based on that information, try to predict a result. And the easiest way for us to think about this is in binaries, so that the patient has a disease or they don't have a disease. So it's breast cancer or it's not breast cancer, or prostate cancer or it's not prostate cancer, or they're going to have a heart attack or they're not going to have a heart attack. And we have some sort of grounded truth. So for all these patients, let's say that we actually want to know whether they're going to have a major cardiac event. We know which of these patients have a major cardiac event or not, and which ones haven't, let's say over the subsequent 10-year period. And so based on all this information, this neural network is going to try to predict, based on the information, which patients are going to have a major cardiac event. So the first patient comes through and it says, yes, they're going to have a cardiac event. Our information says, no, they didn't have a cardiac event in the next 10 years. So we have an error. And so based on that error, it refines it, it back propagates it through the neural network, adjusting the weightings to get closer to the answer. Then we get the next patient. So that was patient 1 of 800. Patient 2 of 800 goes through. And now what we've got is we've got weightings on each of the nodes that is adjusted slightly based on the first patient where we had an error. In this particular case, it might say, yes, this patient is going to have a major cardiac event in the next 10 years. And they did have an event. So now we don't have an error. It was actually correct. So instead of refining and adjusting the weightings, it reinforces the weightings that we've actually got. And then the second patient and the third patient. And what we want is we want to actually have a balance between, it doesn't mean every patient will have a major cardiac event, but between these two groups of patients, the large and the small sample, we want an even distribution. So if 30% of the patients have major cardiac events and 70% different, then we want that represented in the big database and the small database. So we run 800 patients through, and each time we run a patient through, it measures the error against the grounded truth, makes adjustments to the weighting to try to improve the outcome. And that's how we train the neural network. The next part is to then test it. So we're validating it. We're going, well, now we've trained it, let's see if it works. So we don't want to give it the 800 or a part of the 800 studies that we've already done, because it's already seen them, it already knows the answers. So let's give them a new set of data, which is the remaining smaller data set of 200 patients. We feed that information in using the weightings that it's been trained on. We get the results, we compare it to the grounded truth, and we work out whether it got it right or it's wrong. And so let's say out of the 200 patients that we went through, that it actually predicted correct in 180 of them. That means we've got a 90% accuracy. So 90% of the time that it was able to predict whether the patient actually had a major cardiac event or not. And we could even break it down into sensitivity and specificity, so we could look at it from the point of view that if the patient had a major cardiac event, 98% of the time it was the neural network predicted it. And if they didn't have a major cardiac event, then 95% of the time then it predicted that they wouldn't have that event. So you get a bit of an idea of potential false positives and false negatives. And that's essentially what we're trying to do with these neural networks. If the validation phase worked, well, then you could then go into your inference phase where you're actually using it on new data to predict an outcome. So if we break it down a little bit further, just a tad more complex than that. And so here we've got a neural network, and as I said, you could have 150 or more features that are inputted in. In this example, we've just got 4 features that are inputted in. And each of these nodes, they're actually called a perceptron. And this purple little circle up here is what each of those perceptrons look like. And so in the middle here, you've got your actual node, and that node can actually have, so this is what we're going to calculate. It can actually have a number of inputs. So we've got X1 through to X4, which represent the 4 features that we have that are the 4 inputs. So we've got 4 inputs into this node, and each of those inputs can have a different weighting. So W1 through to W4. And you can also have some pre-understanding, some knowledge that we had before that we introduce like a bias. So it's very much like iterative reconstruction, where we're going to go through multiple iterations of learning based on reducing the error associated with your first guess to your second guess to your third estimate, fourth estimate, etc. And we can actually have other information we can input to make those guesses more accurate to start with, and that's our bias. And then from that, and this is all mathematical, these are all numbers, we go through an activation function. So we've got an activation function in there, and then we have an output. And that output Y then becomes the input for every node in the next layer. So you can see that, so this node here, this perceptron here, had 4 inputs from each of these features. It has one output. That one output, Y, goes to each of the 8 perceptrons in the next layer. And then this next perceptron, it has 8 outputs. Sorry, it has an output into the 8 nodes in the next layer. And so that's how it actually moves through. Each one of these purple perceptrons has this process of having these multiple, and so you can see that by the time you get to, in this layer, you have 4 inputs into each node, but this layer actually has 8. So it has, each of these nodes has 8 inputs with 8 different weightings, also has a bias, and then we move through. And so eventually we get to our unscaling layer, which just means it converts the data back from data that the neural network understands into data that we understand, and gives us our output, as I said, in a case of a binary, that they're going to have a major cardiac event or they don't. So through that process, we actually have a loss index which measures the error in terms of whether it's close to or not close to, and there's 2 ways that we measure that. Probably inappropriate to get into that in detail here, but certainly it's contained in those journal articles that I talked about. And then we optimize our algorithm, move it around, adjust the parameters, and then run through the next bit of data. If we reach the stop condition, so it means that the loss index is such that, yep, it meets our demands, and then we can actually do a couple of things, and those are working out the order selection and the input selection. And what we're essentially doing is trying to work out which features to include and how many, what the complexity of the neural network is. So how many nodes and layers that we need to get the right outcome. And so what we can actually do is that if we actually use a decremental order algorithm, then what it means is that once we've worked out what our error term is with our 4 features, let's drop feature 4 off and see what happens to our error. So all of a sudden we actually have an error term that we measure, so the selection loss. When we actually see the error term go up, using a decremental order algorithm, then we know that we've actually dropped 1 too many features out. And then we use a growing inputs algorithm to determine how many nodes. So we keep adding nodes until we actually see an increase in the error. And once we see an increase in the error, we know that the complexity of the neural network has reached its maximum, and that defines then where we stop. And that then defines what our final architecture is. So we might start with this architecture, and then we finish with something that might have 2 feature inputs. It might only have 2 hidden layers, and they might only have 6 nodes in each hidden layer, for example. So then we actually talk about deep learning. The word deep learning is actually related to the depth of the neural network. It doesn't actually necessarily say it's a convolutional neural network. Typically, convolutional neural networks require a deep neural network, but you could actually have a normal artificial neural network that deals with such complex information that is also a deep learning network. So it's about the depth of the network, not necessarily the fact that it's got a convolutional component to it. But in this particular case, is that this is what we're looking at with a convolutional neural network. So we've got essentially an image, and within that input image, we've actually got data, and these are, this is a patch. This white area was what we'd call a patch that we're going to extract. And each of those, within that patch, we actually have a matrix, so counts per pixel. So we extract that, it becomes a convolutional feature map. We run a kernel across it, and excuse me, our typical kernel is a rectified linear unit. And so we run that, and it can be multiple kernels. So typically there's multiple kernels. They're a little bit like lenses. So I can put if I'm looking at an image, I can take an image using a red filter, a green filter, a blue filter, a yellow filter. And so I'm ending up with multiple images that look at things slightly differently. And I'll explain that in more detail a little bit later. And then we can pool all of that information in. We go through multiple convolutions, meaning we get multiple bits of data from that image. And then we flatten that data into a single layer of input information, and that data is numerical. So we're essentially converting this complex image into some sort of numerical representation of that image that can be fed into a neural network. And because the amount of data is so significant going through that process, and you can imagine that if you've got SPECT or PET or MRI or CT data, that you've not just got one image, you've got layers of images as you slice through an organ or the body, and then we forward propagate that through the neural network. So as I said, you got your input image, or we call it an input tensor. We have a patch that we actually run through various kernels, which I'll show you in a second, and they're represented here by the slightly different colors. The rectified linear unit. So we end up with this patch is being represented by the little black dot. So we end up with our feature maps after we've run the kernel over it. And then those are sort of like compressed or shrunk down or condensed via a pooling process. It's usually a max pooling process, which I'll talk about shortly as well. So we end up with a little bit less data to deal with, and then that data is then flattened out. So you see this 2D representation becomes a 1D representation to enter into the neural network. So this is, and I don't want to get too bogged down into the process, and this is not really a deep mathematical dive, but it's just a little bit of a perspective that you'll all understand of what we're actually doing. If we look at this as our image tensor and our patch, right? So this is the patch that comes from our input. And so this is the patch here, is that we're represented by a number of pixels, and each of those pixels has different counts. So imagine this matrix is this patch with a bunch of pixel counts in it. And so what we can actually do is we can apply a bunch of different kernels to it, or different filters. And they're similar to, those 9-point filters that we might run over, a matrix when we're trying to smooth an image. So kernel 1, being the orange one, kernel 1 might be this one, where we've actually got this cross of ones, weightings of ones, and the zeros. So what we're essentially doing is trying to work out how we're going to apply this um, kernel to this kind of data, right? So if we're looking at creating a feature map, this 8 becomes 8 plus 9 plus 7 plus this 7 plus this 12, and we're ignoring the 4, 7, 6, and 6. And so it becomes 43, I think. Mathematically, I think, do the numbers in my head. And then we move to the next one. And so then we would have, so then this would be the 6, and then this would be the 5, and then this would be the 9, right? Applying the same filter. So we'd have 8 plus 9 plus 3 plus 5 plus 6 being 31. And that becomes, that's how we're running the kernel through our data. So that then becomes our feature map, our orange feature map here. And this replaces the patch and represents this little bit that's in the black there, right? So that's what we end up with. Now, of course, we have an orange one, which means it will be a different filter. So it might be, a 2 in the middle, a 1, 1, 1, 0, 0, 0. The green one could be, a much steeper filter using a 9, a 3, and a 1. So each of the filters are a little bit different. To actually, essentially what you're doing is you're looking at the data through different lenses, different weightings at the data. That's run through the rectified linear unit, and then we end up with these feature maps. And what do we do with our feature map to turn it into a pooling? So then we want to pool the data, and the way that we pool the data is that we then say, well, let's actually look at data into larger blocks. So 2x2 max pooling is the common way that we pool this data. So we actually look at a 2x2 array. So this 2x2 array, we actually want to find the maximum pixel. So the maximum pixel within that 2x2 array is 35. So it means that the number 35 will now be used to represent all 4 of those pixels, and that's 35. And then here, we're actually looking for our 2x2 max pooling. It's going to be 31. So 31 is what represents that data. 43 this 4, and 32 for this group of 4. There's a thing called a stride, and what the stride is how far you move your data, whether there's an overlap or not. So when I actually went across this data, so I went, I applied this kernel to 8 and then 6 and then 5 and then 9. So it meant that I'm moving a gap of 1 per, right? So each of these is this is what's replaced 8, 6, 5, and 9. So it's a stride of 1. It means I move 1 each time. But down here on the feature map, I've got a stride of 2. And what that means is that when I actually work out what my next value is, if I had a stride of 1, then I'd be looking at this data and you'd have 35, but then my next group of 4 would actually overlap between 28, 31, 31 to 25 and become 31. And then I'd actually have the next lot of data would then be the 31, 28, 28, which would be, so I'd end up with a 3x3 box, right? I hope that makes sense. But because I got a stride of 2, it means my 2x2 window skips a box. So it skips a lane. So it focuses on this, and then it moves 2 boxes over to do the next 2x2 array. And so this is our pooled data. So we're now getting a representation of the data into a smaller set. So, and then we want to flatten that out. And the way we flatten that out is we want to turn that from a 2 dimensional array into a 1-dimensional array. So you can see that the 43 and the 32, and then the 35 and the 31. So we just flip that vertically. So we rotate it up vertically, and we end up with this 1-dimensional array of numbers. And then stacked on top of that would be the same version of these things with a different kernel, the feature map and the 2x2 pooling to give our orange section, and that would be stacked on top. And that's how we flatten it. So I hope that gives a bit of an idea of the way that convolutional process works. So let's jump into training a neural network. And often you'll actually see presentations from people talking about how a neural network works, and they might say, okay, well, you're trying to recognize the difference between lasagna and endocarditis. And I'm sure you've all seen this. Lasagna, I'm hoping that's lasagna, endocarditis. Okay, so you've all seen that. And some of you would have also seen the chihuahua versus the muffin. Okay, so you don't want to be taking a bite out of a chihuahua. So most of you can recognize those. And just down the right-hand side, a few other images that a neural network might initially have some difficulty differentiating as being different. So we're going to use alligators and crocodiles for training. And so this is the interactive part of the presentation. So this is where if you think the image is an alligator, then you give a thumbs up. And if you think it's a crocodile, then you do a hand clap emoji. And I'll give you the answers as we move along. And this is actually how we train a neural network, right? So this is the training phase. So looking at the image, you get to determine whether this is a crocodile or an alligator, and you need to pop up your answer. Right? So some of you would have said crocodile, in which case you've got it right, and it reinforces whatever judgment decisions you've used to determine that that's a crocodile. Some of you would have said it's an alligator and got it wrong, and so you're actually reassessing what you're doing. And so this is essentially what we do with our neural network. Some of you got it right, some of you got it wrong. You're going to refine that. So if you got it wrong, you change the weightings on your neurons in your brain. So you're changing the weightings on your perceptrons to actually try to come up with the correct answer. All right, so next one. Is this a crocodile or an alligator? Give me your answer. Okay, so it's a crocodile again. So if you actually said crocodile, it's going to reinforce your decision-making process. So it's reinforcing the weightings that you've got on your perceptrons. If you said alligator, then you are going to adjust the weightings on those perceptrons to try to get the correct answer. This one, alligator or crocodile, throw in your answers. Obviously an alligator. So again, if you got it wrong, you're going to adjust your weightings. And so now what we're going to do is we're going to introduce a bias, right? So the bias is like me telling you that an alligator has a U-shaped snout and a crocodile has a V-shaped snout. So now that's a bit of a bias that's going to help our neural network understand. So with that bias, it means that now the neural network has something to look for. So we're looking at this. Is this an alligator or is it a crocodile? So knowing the bias, we're looking at the snout. It looks like a bit of a U-shaped snout. So most of you will say alligator and you'll get it right. Some of you said crocodile. If you said crocodile, well then you need to start to think about more carefully about the bias, but also adjust your weightings to accommodate that bias. Alligator or crocodile. So our bias tells us to look at the snout. Looks like a V. So we're going to go with crocodile and we're going to get it right. Alligator or crocodile, our bias on our node tells us look for the U-shaped snout. We can see that that's a U-shaped snout, so we know that that's an alligator, and so we say alligator. If we said crocodile, then again we would adjust the weightings to try to improve the answer. This one's a bit more difficult because when we look at it, our bias tells us look for the U-shaped snout or the V-shaped snout. We can't actually see the shape of the snout directly because we're not looking from a front-on view, but we get the impression that it's a V-shaped snout, a narrower snout. So we're going to go with crocodile because it looks like it's a V-shaped snout from the side. If you said alligator, well then you'll actually have to change the weightings to try to better interpret a picture of a crocodile from the side. Alligator, crocodile, alligator. And so what we've actually done is we've gone through this process and trained our neural network to be able to recognize an alligator or a crocodile. but now we need to see whether it's accurate or not. So what we have to do is have another set of images of crocodiles and alligators, and now the weightings on our neural network are fixed. So it's actually been through the training phase. So our bias is there, our weightings are there, and now we want to assess with what we've got, how accurate the outcomes are. So we give it another smaller data set to test it. So here we're going through the validation process. So we're going to validate your learning. So each of you can now, and we're not going to give the answers as we go. Is what you need to do is record your answer, and then we test them against the results at the end to determine how accurate you were. So again, thumbs up if you think it's an alligator, or hand clap if you think it's a crocodile. Same with this one. Now this one, and this one. It's an ugly beast, isn't it? Okay, so what we do then is we know that we had two of each, two alligators, two crocodiles. Did you get it correct? How many did you get correct? So let's say you got 3 out of 4 right. Then we can actually test that the accuracy of our trained neural network is 75%. If you got 4 out of 4, then our accuracy of our trained neural network is 100%. And so that gives us an idea of whether our neural network actually is valid or not. Now you need to remember the kind of data you trained it on. So we only did a few small numbers, but you'd be talking about hundreds of patient data sets or hundreds of images. And so, and then the accuracy would have been tested, or the validation would have been done on a smaller number. It could have been 100 or 150 other images. And so it's really important to sit there and say, well, what do those images represent? Because if all of those images represent an internal environment or a specific population, well, then our accuracy of that neural network relates to that population only. It doesn't mean it has external validity outside of that population. And so this is where we need to start thinking about where we collect our data from. What's our data represent? Who does it represent, and what is the results valid for? So the majority of the research that we're reading in journal articles at the moment around artificial intelligence in radiology and nuclear medicine actually relate to the training and validation phases, not the inference phases. There's a few that talk about the inference where they've actually initiated and implemented in practice, but most of what we see in the journal articles is related to this training and validation process. So let's talk about some of the applications. So we can talk about image classification, which predicts the class of an object. So for example, is it a lung tumor on a chest CT, as we can see over here on the far left. Object localization, so it uses a bounding box like this red box that we can see here to define the spatial parameters of the object. Then we can actually do object detection, which really determines multiple objects and classes. So we've got a bounding box in red around the tumor, and a blue bounding box around liver, and purple bounding box around kidneys. And then we can actually do instance segmentation, where we actually fit the region. So we get this auto segmentation that actually defines, not just in 2D, but in 3D, the limits of whatever those objects are. And then what that allows us to do is actually create class labels for those. And so how would segmentation work with the neural network? So obviously you have an image, and we have a number of complex and related but overlapping structures. So obviously we go through a convolutional process. So we've got this convolutional neural network that pulls out this image data and converts it into pooled feature maps. And those pooled feature maps can then be used for region of interest alignment before it is flattened, goes through a neural network to create a class box. Okay, and then, but at the same time, that pooled feature can be flattened before, independently of that region of interest, flattened and go through your fully connected layers to go through a classification process. And by combining the classification and the class box into a process, you end up with, your defined answer. So you've got segmentation of your tumor and then classification of the outcome. So two neural networks working together. So it introduces this idea of computer-aided detection and computer-aided diagnosis. So CAD E with the little e is computer-aided detection. So that represented in this image by the blue boxes. So you've actually got your image recognition. From that, you can have localization with your bounding box. You can have image classification from your image recognition and then object detection. So that is your computer-aided detection. And then you have the computer-aided diagnosis, which then includes the green part, so object segmentation and then object class. So as I said, is that neural networks are not new in nuclear medicine. Is that back in 1993, Scott and Palmer had 28 input parameters using a 15-node single layer neural network, and they trained on 100 VQs using angiography as the gold standard, and 28 new cases were used to test it, and they actually sort of showed that it performed comparably to experienced nuclear medicine physicians in determining whether the patients had pulmonary embolism or not. More recently, we've seen a number of applications emerge in nuclear cardiology, and this is a study using over 1,100 patients, and they use an artificial neural network, specifically convolutional neural network, which improved automatic interpretation. So they were comparing it to on a basis of per vessel, but also per patient basis to perfusion defect scores. And they used the area under the curve of the ROC analysis, where the more area under the curve, the more accurate it is. So obviously our red curves, both of our red curves have slightly more area under the curve, so it's more accurate than the blue curves. But what we need to remember in this is that what are we actually comparing it to? We're not actually comparing the deep learning algorithm to making decisions against a human observer. We're just saying that the deep learning process is better than relying purely on the total defect perfusion defect scores. So we already know that the defect scores are not 100% accurate. So we would never rely on the defect scores alone to determine whether a patient had coronary artery disease or not. And so to outperform those, every physician would outperform the total defect scores. So it's not saying too much against how it performed against a physician, but we shouldn't be competing with physicians anyway, because the reality is we need a human in the loop to make decision making. So it should be being used to actually help the physicians make decisions. And so what I like about their project is that the way they actually integrate the deep learning into what's already known, so our existing radiomic feature displays. So here you can actually, and I think this is the reason I display this, is because I think this is what we're going to see more of in the future, where how do we integrate our deep learning algorithms and outcomes into our semantic and radiomic analysis. And the way we're going to do it is using the same model. So here we're using polar maps to represent our data, and this polar map down the left hand side is our total defect perfusion defect scores. So this is what we're actually comparing it to, and it's looking at the total defect scores of 0.5 in this zone. So obviously that's the left anterior descending, and 0.3% is the total defect score in our right coronary artery, to give a total perfusion defect score of 0.77%. So what that's saying is that there's about less than 1% of the total blood supply is affected. And so using that same polar map is that we can actually use a deep learning algorithm that gives us a probability. And so it's a probability of coronary artery disease. So we've got 62% probability of coronary artery disease in the LAD, and 20% in the right coronary, and 33% over here in the left anterior descending, the left circumflex. And so this is the way that we'll actually see those deep learning outcomes displayed. The patient on the right, triple vessel disease, total defect score 12%, whereas the deep learning algorithm showed an 84% probability of the patient having coronary artery disease, specifically in the left circumflex. So I really like the way that this is displayed, and I think that we need to be thinking about how our outcomes of deep learning can be massaged into these kinds of displays, either for small data using our local projects, or using standard software that might be produced by some of our either software developers or our gamma camera and PET scanner vendors. And when it comes to segmentation, the image on the right is 5 regions of interest drawn around the same tumor by 5 different people. And you can see they're all very, very different. And as a result, the SUVs are different. If we actually use segmentation using artificial intelligence, then what we'll end up with is maybe a 6th region that's a little bit different again. But the advantage of machine learning is that each time it draws a region, it's going to be more consistent. So the artificial intelligence takes some of the subjectivity away from the segmentation. The guys down at Peter Mac published a paper a couple of years ago where they're using a convolutional neural network to auto-detect renal contours through complex CT and PET images. Obviously, manually drawn regions are very time-consuming, especially when you're doing across multiple studies, and it's being used for, obviously looking for kidney dose in radiation dosimetry associated with lutetium PSMA scanning. And you can see that the training versus testing accuracy, so the training accuracy was quite good, the testing accuracy not quite as good, but still close to 95%. The regions performed fairly well. What they found is that the automated regions matched the manual regions most of the time, except when there was some disease of the kidney, in this particular case up here with case 5, some polycystic kidney disease. One of the other applications that is widespread in the current literature, I think there's about 3 or 4 articles been published in the last 3 months or so, looking at the development of a pseudo CT instead of doing CT. Now, if you're doing PET CT or SPEC CT, then you've probably already got the CT. It's not that big a deal. But if you're actually invested in PET MRI and you're not really all that happy with the MRI attenuation map, because there are some limitations associated with the MRI attenuation map, then instead of actually trying to muck around with how you develop an attenuation map from the MRI, then we can use a convolutional neural network that uses a combination of the MRI and the PET data as an input to create a pseudo CT. And so in the training phase, you would actually go through this process of multiple patients having MRI and PET that would produce a pseudo CT, and you would compare it to the actual CT for that patient, look at the error, make the adjustments to your weightings to learn, and so you'd be going through that training phase. And once it had been trained, then what you're essentially doing is you're actually using your pseudo CT without any CT to do your co-registration and attenuation correction and iterative reconstruction. Obviously reducing the patient dose as well. I mentioned before that some of the higher end types of applications up in the violet zone of our spectrum is looking at image reconstruction. And so instead of using filter back projection or iterative reconstruction, we can actually use an encoder decoder structured neural network. So this is a very deep convolutional neural network and this is sort of like the rough structure. The colors represent the different processes. So you can see that pink is convolution with a stride of 1, purple is a convolution with a stride of 2, batch normalization is the blue, activation function is the green, and then upsampling. So on the other side, because the encoder part downsamples and then upsampling back to our image on either side. And you can see our feature layers and convolution depth. And so we're feeding in a sinogram basically. So you go through this encoder phase and then the decoder to actually reconstruct your slices directly from the sinogram rather than using filter back projection or iterative processes. You can also use an encoder-decoder neural network to denoise images. So in this particular case, you're training it based on input from CT and MRI, or CT or MRI, going through the encoder-decoder process to compare your estimated PET to your actual PET, looking for an error, training it in that fashion so that we actually get the right balance of weightings, so that in the inference phase, what we're essentially doing is simply just producing these denoised PET studies. And I think that one of the exciting applications of that kind of structure, again, the encoder-decoder setup, using the graph neural network module down the bottom, is basically using, and this design is called a UNet. So it's a specific type of neural network that you can actually search for and download the code for. So that UNet architecture is basically, you can use it to develop dosimetry-based optimization for therapy. In this particular case, I'm using your lutetium-177. So essentially, what you're doing is you're saying, we actually have a bunch of serial lutetium scans done on gamma camera, so we know what they are, and we're actually looking at an input from a gallium-68 PSMA scan, and through our neural network, we're actually estimating what the dosimetry is, and we're estimating that dosimetry based on the gallium and comparing what we've determined it to be, including the entire kinetics of that dosimetry, to what we know has occurred using serial lutetium-177 scans. Now, I know that because you can image the lutetium anyway, that we can use that to calculate it along the way. But the advantage of this process is that we're actually trying to optimize. We're training our neural network to be able to predetermine our dosimetry based on the gallium being trained against the serial follow-up lutetium scans. And if you can get that accurate, well, then what it means is that instead of actually having to adjust your doses to the patient, your lutetium doses to the patient for your second, third, or fourth round, based on what you saw in your first, second, and third round, then you might be able to make those earlier predictions based on your gallium PSMA scan. So it's kind of exciting opportunity to improve your dosimetry, particularly with that first dose. And so when we talk about precision nuclear medicine, this is what we're really thinking about. We're thinking about how all of this ties together. So we have our small data that's part of our department, our patient data and our functional imaging and our radiomic feature extraction and molecular imaging, including the machine learning we might do in our department with our small data. And we're actually implementing that, but we're also plugging it into potentially big data associated with multi-center and multi-site trials to create this deep learning associated with data mining and neural networks. And that will feed precision nuclear medicine and optimize our outcomes generally. So there is some caution I wanted to quickly touch on associated with convolutional neural networks. And we've seen this diagram before, so we think about just reminding you of the process and these convolutional pooling steps. But what occurs is that what you actually see is that people are getting excited, particularly in radiology, about the opportunities. And we've seen a number of articles come out where we're actually seeing artificial intelligence, the deep learning algorithms, outperforming a radiologist. And you sort of ask, well, how can a radiologist not be as good as a deep learning algorithm if it's learning from the radiologist? Right, so there's a couple of these in pneumothorax, and these two are in pneumonia, where the deep learning algorithm identifies pneumonia more accurately than a radiologist. So how does it do that? Well, the first thing it does, and these quotes come from a presentation by Elliot Siegel, and so I've sort of reproduced those in different ways. But Geoffrey Hinton, who's a bit of an AI guru, has used these kinds of algorithms and their performance to signal the end of radiologists. So he's sort of saying that that radiologists are coming to the end of their life, their usefulness, and he thinks they should stop training radiologists now. And then there's a CEO of a big medical imaging startup who actually refers to radiologists as wasted protoplasm, which is a little bit insulting, but that's their view on the role of the radiologist moving forward. And that rings alarm bells for radiologists. It drives a little bit of skepticism and resistance for AI. No one wants their role taken over and becoming redundant. But the truth is that it's nowhere near the truth, and I'll show you why. But just before we do, reflecting on what Elliot Siegel has sort of said is that, what's the point in having this, getting excited about technology that can make the same mistake but faster? So if all we're doing is making mistakes or wrong decisions faster, then we're not really advancing. And so we need to be really mindful that one of the things that we don't know is that when we actually have a deep learning algorithm that says with 75% certainty that a patient on a chest x-ray has a central line, that as humans, we don't know whether that algorithm found or saw a central line or whether it simply identified a patient who should have a central line based on the disease they have. So we don't know. And so, these algorithms that we're worried, that people like Geoffrey Hinton think are so good that just taking over the world, may not be as good as we think, and there needs to be some caution. And the images below, again from Elliot Siegel's presentation, show a really good example of an algorithm on the left that looks at this image and classifies as a panda with 60% confidence, and then we add a little bit of noise to it. So the image in the middle, we add that noise to this panda image. And then for me, when I look at the image on the right that includes that noise in the background, it doesn't change. It looks identical to me. I'm still very confident that's a panda bear. But the image analysis, just because there's slight bit of noise that visually I can't even see and appreciate, it changes classification from a panda to a gibbon and increases confidence from 60% to 99%. And that tells me that there's a significant flaw in that deep learning algorithm. So let's think about a chest x-ray. And I'm doing this from a nuclear medicine perspective. I'm not a radiologist. This is very rudimentary. And I don't want to insult radiologists. I'm sure they look at things in far more depth than what I'm going to do. But just to paint the picture, is that how do we look at how do humans look at a chest x-ray? So when we're looking at this chest x-ray, we're looking at the red zones, we're looking for the lung fields, and then within the lung fields we see that over here in the blue zone we've got this consolidation that looks different to the rest of the lung, right? And so we're going, okay, this is what we're looking at. So how does AI look at this same x-ray? So first it looks at the red zone, it looks at the blue zone, but it also looks at all these green zones. Right? So when it decides whether this patient has pneumonia or not, it doesn't just look at the chest. It goes, oh, it's Dr. Jones again. 70% of patients that Dr. Jones sends, based on the AI's data, have pneumonia. So it means that because it's coming from Dr. Jones, I'm going to increase the probability that this is pneumonia independently of what's in the chest. Then it looks and goes, oh, the patient was done supine. So if the x-ray is done supine, it means the patient is less well than if it was done erect. So a healthy patient is done erect. So because this patient was done supine, there's a greater probability that they have pneumonia. So I'm going to increase my probability that the patient has pneumonia. The patient was done mobile, so they're too sick to come to the department. So again, I'm going to increase the probability that the patient has pneumonia. And then they're in critical care. That increases the probability that they have pneumonia as well. And then I'm going to look at the age of the patient, so they can see the X-ray shows a bit of degenerative joint disease, and so they're older. So if they're older, they've got a higher probability. So on this X-ray, the AI picks up 5 very important pieces of information that are completely independent of what's going on in the lungs, that it will actually increase the likelihood or its prediction that the patient actually has pneumonia. So independently of what happens in the lungs, it's going to call it pneumonia because it has 5 high risk things that it's identified independent of that. And this is the flaw. It's not seeing pneumonia, it's predicting it based on other things. So do we need to actually adjust the way radiologists think about it? Should radiologists be using these same probability markers to determine, so you have a perfectly clear chest X-ray, or the radiologist can't see anything that looks like pneumonia, but because it was referred by Dr. Jones, it was done supine as a mobile from critical care, and the patient's 65 years old, should they just be calling it pneumonia just to cover themselves? And that would increase the sensitivity, which is a little bit weird because, you know, it's not what they're actually seeing. They can't see pneumonia, they can't see evidence of pneumonia, but probability is the patient has pneumonia based on these other factors. And if you think I'm joking, then here's the heat map. And so this is from that deep learning algorithm that was published. And so what these boxes indicate is that the higher the number in the box, the greater the weighting that that area has in determining pneumonia. So as you can see, is that the fact that where it says portable, semi-erect, this area over here, completely outside of lungs, so soft tissue. These areas are all indicating, providing a higher weighting to determining whether the patient has pneumonia than many of the areas actually in the lung fields themselves. Another example, and you can see that the ECG dot or the ECG lead provides the highest weighting to suggest the patient has pneumonia. So it's not what's in the lung, it's the fact that the patient has an ECG on them that says that they're less well, it was done portable, and so they're more likely to have pneumonia, independently of what you can see in the patient's lung fields. So that's kind of frightening. And what it means is that the doomsdayers that sort of say, you know, radiologists are gone, are barking up the wrong tree, because you need humans in the loop. You need machines can look at the big data, they apply their AI, they provide possible actions, but you need a human in the loop to make those judgments and decisions that that optimize the outcomes for the patients, that make sense of it all. And as Charles Kahn has indicated, and he writes a really good blog around AI, and then it's called what's it called? The Vasty Deep, which I think is a Shakespeare reference. One of the ongoing challenges of AI is to develop systems that can explain their reasoning, or at least allow humans to interpret their output. And that's the challenge, is that we don't understand how these machines are getting their answers. So future opportunities, we've been through a few of them, but this is what I'm thinking that we should be seeing in our departments. And these are mock-ups, these are not real. But this is what I'm thinking we should be seeing, is that we should be developing either in-house or as part of our vendors, developing software that comes with their gamma cameras and PET scanners. These interpretation algorithms that don't just display our ventilation perfusion lung scan, but they actually draw, they segment the lung and identify regions that are high probability, so red being almost certainly a defect, through to purple being improbable, and then providing some sort of probability score, in this case around pulmonary embolism. So we've got a 99% probability that there should be pulmonary embolism. So this is the kind of display that I think we should be moving towards in nuclear medicine. Here's another example with perfusion SPECT and the CT that goes with it. So this is non-diagnostic CT, but the patient on the left, where you've got a perfusion defect, drawn, identified in the same region where there's no defect seen on the CT, so clear airways, and so that would indicate a high probability of pulmonary embolism versus the patient on the right, where you've got a defect that has an area of consolidation on the CT where that's not perfectly normal, but it's a much lower probability of pulmonary embolism. And even bone scans, where you actually see a bone scan that then is mapped, you get auto segmentation, and then scoring not only of the probability of a individual defect being met, but an overall metastatic disease burden. So you get a numerical value that talks about or talks to the actual disease burden of the bone scan. So these are the kinds of things I think we have a real opportunity to develop in nuclear medicine that change the way we do our daily practice. So as we start to get to the end, we need to think about, the limitations, and the liar paradox from Star Trek is a really good example of how AI doesn't think pragmatically. It defies anything that defies first order logic, confuses AI, and so that's why it can't be used for decision making. If this is a robot in the middle and someone says everything Harry says is a lie, and then Harry says I'm lying, then that creates a paradox that the artificial intelligence can't understand. For the same reason, it doesn't understand humor. So that pragmatic humor that humans enjoy or sometimes enjoy, AI can't differentiate. And so we start to think about how we might actually change that, because when we're thinking about those nodes, those perceptrons, their binary is that they're either 1 or they're 0. Of course, they come with weightings and outcomes, but they're operating in a sort of a binary mode. Whereas if we think about quantum logic and quantum neural networks, then we might be thinking about a qubit instead of a node that can actually not only exist as 0 and 1 at the same time, but it can exist in all different directors at the same time. So we're talking about dividing those into basis vectors. So if we think about that pragmatic joke, you can interpret the fan in 2 different ways, that we end up with using quantum probability theory, that these basis vectors, each of those vectors represent a different way of interpreting the information. And that way we might be able to develop synthetic intelligence that plays a more important role in decision making. Excuse me. But when we think about the workforce implications, because this is the biggest barrier, I think, people, concerned about, being replaced by AI. Well, it's not going to happen, as AI has been around for a long time and it hasn't replaced anyone yet. It's not like the darkroom, moving from, the processor technology to dry technology that made people like the darkroom technician was made redundant in that process, but it didn't make radiographers or nuclear medicine technologists redundant. The computerization hasn't made those people redundant. And so when I actually stopped and thought about the structure of a department, if we looked at a department that looks a little bit like this column here, that might be a public teaching hospital, you've got 4 physicians and a couple of physicists. You're not going to have a data scientist in those departments at the moment. You'll have a radio pharmacist, 9.5 techs. The other half of the tech operates as the PACS manager, a couple of nurses and a few research fellows and PhD candidates. If we converted that department to something that was fully immersed in artificial intelligence, so they're doing AI associated with clinical, but doing some research as well, then it's not going to change the number of physicians you have. It might change the number of physicists you have. So you might actually convert a couple of those physicists from being physicists to being data scientists. So you're not losing the number of staff, you're just changing their work function. And the same with the technologists. One of the technologists may change work function from being a technologist to being a data manager, because you're dealing with, it's not just a matter of PACS administration now, you're doing true data management and data mining. And you might end up with more research staff. So I don't think from an employee perspective that it's going to change the employment, what you might get is a change in roles for a small number of people that have the inclination to get involved in data management and AI. And so when we look forward at the future, while I think it's unlikely that people in nuclear medicine will be displaced by AI, I think that staff members who have AI capability, like you all now after you've listened to this presentation, are more likely to displace those that are disengaged with AI. And I think that's what will make the difference. If you're going to employ someone in the future, if they're completely resistant to AI and everything that goes with it, they're less likely to be employed than someone who is actually immersed and engaged in that discussion. That's not today, and it's not even tomorrow, but it will be the future. So what are we ready for today? So today we should be doing our imaging tests. We've already talked about that semantic evaluation by the physician and in combination with the radiomic feature extraction. And then I think what we actually have is this pre-analysis and data extraction that AI might help with. And then we'll actually be running our results through things like an artificial neural network or a deep neural network for simple studies. Some of our more complex data like CT and MRI and PET and SPECT, using our deep neural networks and convolutional neural networks, there's some applications there as well. So we'll use those neural networks to improve our outcomes, but more importantly than just improving our outcomes, we'll use them to learn. And by using them to learn, it'll actually improve both our radiomic side of the analysis as well as our semantic analysis. So it creates this cycle of learning and improving outcomes. So that's the end of the presentation. Obviously, if there's any questions, the best place to put them is up on the RAINS Facebook page. But if there's questions that want to get posted on the YouTube link for this video, then I'll see if I can get around to answering those when I see them as well.